In this video, I'm going to be working through the mechanism to create an alkene. Our starting reactant is an alcohol. This is an example of an elimination reaction because we're eliminating water from the alcohol to make our alkene. As always, there are many ways to do this. We might pass an alkene vapor over an aluminium oxide catalyst at 300 degrees C, or we could heat our alkene with concentrated sulphuric acid. The acid is behaving as a catalyst. And we're heating it under reflux. Let's have a look at the mechanism. Now, there's a reason why I am going through so many mechanisms, and that's because the more you see, even the weird and wonderful ones, the more confident you are going to become in applying what you know to unfamiliar situations, particularly in exams. So there is our alcohol. We have got propan-2-ol. How does the catalyst work? Well, sulphuric acid, H2SO4. If it's not dissociated, then this is what the molecule looks like. We have got hydrogen and oxygen, so we've got an OH group. Oxygen is bonded to the sulfur. The sulfur is bonded to another OH group and double bonded to two oxygen atoms. So that is the structure of sulphuric acid. We've got delta negative oxygen. We have a very delta positive hydrogen. It's very easy for sulphuric acid to lose that proton, as we know. That's how it behaves as an acid. So in this mechanism, one of the lone pairs on the OH group of the alcohol attacks the delta positive hydrogen in sulphuric acid, and this bond breaks heterolytically with both the electrons staying with the oxygen. We are going to have an intermediate, several intermediates in this particular reaction. So we've got our methyl group, our carbon, hydrogen, another methyl group, and at this point here I have an oxygen bonded to two hydrogens, so it is positively charged. It's electron deficient. It's used one of its lone pairs to make the bond to the hydrogen. What's it going to do? Well, this makes it a very powerful leaving group. So it leaves as H2O, taking both the electrons in the oxygen-carbon bond. And as a result, we end up with this carbocation. We do like a carbocation. So CH3, CH3. Now I'm actually going to draw out this particular methyl group in full. You'll see why in a minute. In the next step of this reaction, we need more of our sulphuric acid behaving as a catalyst. So where should I draw them? I'll draw it over here. So O-, sulfur, double bond oxygen, OH group. Obviously, I hope you can see that this is the ion that was the result of that particular sulphuric acid molecule having its hydrogen nicked. This negative charge is used to make a bond to that hydrogen. That in turn causes this hydrogen to leave, and the pair of electrons essentially flips from the carbon-hydrogen to the carbon-carbon. So one causes the other. It's a very quick knock-on effect. As a result of that, we would end up with sulphuric acid catalyst being regenerated. So that fits neatly with our understanding of how catalysts work. And an alkene. We've got carbon, hydrogen, hydrogen. We've now got a double bond, carbon, hydrogen, and our methyl group. So let's be very clear here. The electrons that made up that carbon-hydrogen bond become the pi electrons in the carbon-carbon double bond of our product. And as we've seen before, we get a change in geometry. So where we did have tetrahedral arrangement around central carbon atom, we end up with a planar arrangement. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the blurb below, it will take you straight to the Crunch Chemistry School, where you'll find all the resources you need to get that A-star grade at A-level. Together we can do this.